All right, how's it going, guys? I'm going to do example 18 in your book with you today. And if there's extra time in class, you guys can work in a group um, on the homework problems that are related to the what we've been doing in class the last couple of days. So in example 18, we have a rather complicated system. We've got a pulley um, that's connecting two blocks, and the weight of one block is causing another block to move up an incline. And so let's read the problem real fast. It says block 1 is moving on a frictionless 30-degree incline. This block is connected to block 2 by a massless cord that passes over a massless and frictionless pulley. Find the acceleration of each block and the tension in the cord. Okay, so the first thing that we want to do is draw a free body diagram for each block. So for mass 1, the free body diagram in this case, I have tension acting up at a 30-degree angle, and I have weight acting directly downward, and there's no frictional force, so that would be it on mass 1. On mass 2, I've got the tension force acting up, and I've got the weight acting downward. And that would be it for the forces on mass 2. Because the rope is massless and the pulley is massless and frictionless, we know that the tension in the rope is the same throughout. We also know, because the rope isn't stretchable, that any change in x for the first block is going to be equivalent to the change in x for the second block. Meaning, if the block on the ramp moves 1 inch, because it's connected by the same non-stretchable string, the second block is going to move down by 1 inch. By this logic, we know that the acceleration of block 1 is going to be equal to the acceleration of block 2, or at least the magnitude will be the same. For those of you guys at calculus, you could do a more rigorous proof of this by taking two time-based derivatives of the position equation that we set up. And that would give you that their accelerations should be the same. So the way we're going to solve this problem is we're going to set up a net force equation for mass 1 and mass 2 based on the information that was given. So for mass 2, we know that the net force in the y is equal to the tension minus the weight, which is going to be mass 2 times gravity. And that's going to be equal to mass 2 times the acceleration. And in this case, that acceleration is pointed downward. So we could actually put a negative sign to show that the acceleration is pointed downward. For mass 1, the net force, I'm going to call the x, but the net force along the incline, up the incline is the force of tension, down the incline if we're looking at this block, we're going to rotate the coordinate system here so it's like that. So up the incline is the force of tension, down the incline is a component of gravity, perpendicular to the incline is another component of gravity, and then we have the normal force. So this is going to be the weight in the y, and this is going to be the weight in the x. So along the incline we have the force of tension, the weight in the x, and that's going to be equal to mass 1 times an acceleration, and since I defined up the incline as positive, we'll write positive A. The net force in the y, in this case, would give me that the normal force minus the weight in the y is equal to 0, since it's not accelerating perpendicular to the incline. This bottom equation would be useful for us if we needed to determine a friction force. Because there is no friction, the top equation doesn't depend on the normal force, and so we don't necessarily need that equation, but I included it just to be thorough so that you can see the standard procedure. We can solve this first equation for the tension and say that the tension is equal to mass 2 times gravity minus mass 2 times the acceleration. And we can solve this equation for tension, and we'll get that mass 1 times the acceleration plus the weight, the x component of the weight. In this case, the x component of the weight is mass times mass 1 times gravity times the sine of the incline. If you're not sure why we used the sine instead of cosine, go back to the notes that we took about rotating a coordinate system along an incline. So the x component of the weight is mg sine theta, and so we've got that solved there. I'm going to set both of those equations equal to each other, so I'm going to get mass 2 times gravity minus mass 2 times acceleration is equal to mass 1 times acceleration plus mass 1 gravity sine theta. Now the only unknown is the acceleration, so I can solve for it. So I'll have mass 2 times gravity minus mass 1 gravity sine theta is equal to mass 1 times the acceleration plus mass 2 times the acceleration, and then just factoring some stuff out, I'll get mass 2 minus mass 1 times sine theta times g over mass 2 plus mass 1 is equal to the acceleration. And we can plug the values in for those, and we're going to get that the acceleration is equal to 5.89 meters per second squared. And if we plug that back into one of the tension equations, then we can find that the tension is equal to 86.3 newtons.